Thank you. Well, thanks, Steve, and for inviting me to give this talk. Start off by saying don't be put off by the rather technical sounding title. I knew Sam, as Steve said, mostly through the GFD course that I taught in. It's a level 5 final year course for master's students. Sam took it in 2021. And I wanted to talk about something that was somehow connected to that. So this title, let's see. Oh yeah. So this is work that grew partly from that module, also partly from my own research interests. And if you're not a GFD specialist, don't worry. I'm going to go through a lot of the basic concepts. A lot of the things basically straight from the module, the Geophysical Fluid Dynamics module. So hopefully in half an hour you'll know something about GFD if you don't already. But essentially there are two key elements that are in geophysical fluid dynamics, apart from the equations of fluid motion. So rotation, because of the planet rotation, and stratification, density stratification in the vertical. And the combination of these two things in the dynamics leads to this quantity called potential vorticity. It's a key quantity in geophysical fluid dynamics. I'll define it. I'll talk more about it later. But it's basically, if you know what vorticity is, spinning around of fluid particles, it's a measure of that spin that also takes into account the rotation of the planet and the stratification, the density stratification. So this is a key quantity that's going to appear throughout this talk, and I'll define it properly soon. There are different wave motions that we look at in the module, in the Geophysical Fluid Dynamics module. And basically, you can think of fast waves and slow waves. The fast waves are inertia gravity waves. The slow waves are Rossby waves. And we do a lot of linearization and looking at dispersion relations of these waves in a variety of models. And one of the key models that we use, or the sort of key model that basically has both of these wave motions, is this shallow water model. So I'll talk a little bit about that. And then that's still not quite simple enough, right? For some reasons, for some situations, we want to look at an even simpler model, and that's the quasigeostrophic model of the title. And I'm going to be basically doing a comparison between the shallow water model and the quasigeostrophic model. This one. Okay, so just a bit more about these different waves and the different ingredients. The fast waves, as I say, these are called inertial gravity waves. And they don't have any potential vorticity. So in the linear system, if you take the potential vorticity and linearize it, and you look at the wave motions described by the inertial gravity wave dispersion relation, you find that there's zero potential vorticity. Okay, so that's fast waves. In the lecture course, when I introduce these, we look at, I give them a density profile and ask the students to calculate the phase speeds or the wave frequencies of these waves, and we come up with something like 10 minutes, and I ask the students, usually, before I talk about them as being fast waves, do you think these are fast waves or slow waves? Okay, and everybody knows that it's a trick question, but they humor me and they say, oh, it's slow, right? You think 10 minutes for a wave to go up and then down. It seems very slow, but the point is, relative to what? And if you're thinking about geophysical systems, weather systems, these things are evolving on the time scale of days, or the planetary rotation is a day. 10 minutes is fast compared with that. Okay, so the slow waves are really waves that are evolving on these slower daily time scales, and so Rossby waves. And these waves, so you contrast them with the fast waves. The fast waves have no potential vorticity. Rossby waves basically have arbitrary potential vorticity, except that potential vorticity must be in something called geostrophic balance. Okay, so this is another key concept. I'll define this properly next slide. All right, so Rossby waves are inherently bound up with potential vorticity. They exist on gradients of potential vorticity. If there's no gradient, there is a Rossby wave mode, but it's not doing anything. It's basically zero frequency in that case, so stationary. But if there's a potential vorticity gradient, then there's non-trivial Rossby wave dynamics. And the nice thing about the shallow water system is that it contains all three of these modes. The exclamation mark is because I've listed two, but the point is there are two fast modes, right? There are two fast waves propagating in different directions and one slow Rossby wave. Okay, so shallow water contains all of these, and it's a nice system. We don't have to worry about vertical propagation. It still has some component of the stratification because that's a free surface. Okay, but it's still too complicated in a sense. I mean, you can do it, but to study the Rossby waves is easiest if you basically get rid of the inertial gravity waves altogether, filter them. And this is the quasi-geostrophic approximation. So it filters the fast waves, and it allows you, so if you've got a potential vorticity gradient, it allows you to linearize around that potential vorticity gradient, and you can get a nice simple dispersion relation for your Rossby waves. If you don't do that, then it's hard to do. Okay, so this is what the system actually is. This is the shallow water system. It's two equations for the horizontal velocity, u. The first two terms are an advection following the fluid parcels, the usual material derivative. It's driven on the right-hand side by a pressure gradient, basically, which is proportional to the free surface gradient. And this term here is the Coriolis term. U perp is the vector perpendicular to the velocity field. So it's the force, effective force of partial fields due to the rotation of the planet. And the geostrophic balance that I mentioned on the last slide is basically a balance between these two terms. Okay, so you neglect the acceleration following the parcel and balance the pressure force with the Coriolis force. And that's what you see on weather systems with the flow going around low pressure centers or high pressure centers. Okay, so that's a dominant balance in GFD. The other equation is just a mass conservation equation. This is the divergence of velocity, flows coming in, the height. The free surface must go up. So it's a system of three equations, three time derivatives, and that gives the three wave motions, the two fast and one slow. Now you can combine those. If you take the curl of the momentum equation, you get vorticity equation. You can combine the vorticity and the height into this potential vorticity that I said. The potential vorticity, zeta is the relative vorticity, F is the background planetary vorticity, the Coriolis parameter, and H is some measure of the stratification, the height. So that gives you your potential vorticity. And the combination of these implies that the potential vorticity is conserved materially following fluid parcels. Okay? So that's a very nice, simple equation. It's a great simplification from the original equations. But of course, it's not complete. It's a single time equation, single d by dt equation, whereas before we had three. So it's not going to describe everything. And in fact, it only describes the balanced motions, the Rossby waves. Okay, so you need to supplement this either with equations for the unbalanced motion or a balanced condition. And a typical balanced condition might be the geostrophic balance. Okay? So you can put all that together and get the quasi-geostrophic approximation. It basically comes from the potential vorticity by expanding the height field. So you assume that there's a mean layer depth plus a small perturbation from that, and you Taylor expand that height. And you assume your dynamics is given by this advection equation, and you have to do make some other approximations. You can assume your Coriolis parameter, the linear gradient of planetary rotation from pole to equator, is basically a linear gradient. And then you do your expansion, and you get this. So there's the advection equation again. And here's what your potential vorticity has become. So you've got your background planetary vorticity, your linear gradient, your relative vorticity, and then some other terms. Okay? And geostrophic balance, you're going to close this system if we go back to the geostrophic balance, the balance between the Coriolis term and the height, the pressure gradient. You can sort of integrate this up, and this defines a stream function for the flow. Okay? And that gives you your U, so that closes the system. And you can express the height perturbation in terms of the stream function. So everything's closed now. So you've gone from a full shallow water to a single potential vorticity. And of course, you drop some of these terms. In the Taylor expansion, you drop everything from there onwards. Basically, you typically keep this term. And it's valid under certain assumptions. The Rossby number, a measure of the flow speed over FL, L's a length scale. That must be much smaller than 1. Relative vorticity is smaller than your Coriolis parameter. The extent of your domain in y, latitude, must be such that beta y remains of the same order as the relative vorticity. So you treat beta y and zeta on the same footing, smaller than f. And also there's a condition on the Froude number, so u squared over gh, that so that this h prime term is small. Okay, so that's the full set of conditions for this truncation to be valid. Okay, so single equation supports the Rossby wave mode. You can linearize it. Everything is nice and simple, and we looked at this more in the course. Look at different cases. Okay, so that's GFD sort of in a nutshell thing. So that's great, but first, various questions. Is this model any good? Right? How good is that approximation? Especially if you go to situations where your Rossby or Froude numbers aren't that small. And what about this restriction in latitude, right? That your beta y term must be same order as your vorticity. It would be nice in some situations to have a model, balance dynamics, that you can integrate on the whole sphere, right? Solving large-scale general circulations. In the tropics, so F goes to 0 in the tropics, and your geostrophic balance, this thing, is not going to give you anything. Okay? So various issues, your Rossby number goes to infinity. Various things we'd like to push beyond that nice, simple situation. And the usual advice is, especially for this last one, don't use QG in the tropics, right? There are other models that you can use. QG is just not suitable for tropical dynamics, which is partially true. But anyway, so let's just try it, okay? So we're going to take the QG model, the advection equation, and in the potential vorticity, instead of replacing the full Coriolis parameter, 2 omega sine phi, by linearizing it, we're going to retain that full latitudinal dependence. Okay? We're going to retain the full f in this relation between the stream function and the height perturbation. Okay, which is not good, right? When we derived that relation between the stream function and the height, we basically integrated geostrophic balance. If f is varying in space, you can't do that. So this is ad hoc, to say the least. Okay, but you do it. This is the potential vorticity that we had before, and that's replaced now with this thing where the f's are the full Coriolis parameter. And before we grouped the beta y with the zeta, now we're sort of grouping the beta y with the f naught by just keeping the whole f. Okay, and we're still neglecting the zeta term, but keeping the beta y term, so we're not doing things in any sort of consistent manner. Okay? Anyway, we're going to take this model, call it the global quasi-geostrophic model, and ask, is it any good? And yeah, is it any good for anything? Does it just die horribly at the equator? So That before, this isn't my creation. There's a couple of papers in 2009, Schubert et al. And Verkley studied this, but it goes back beyond that. It goes back to the early days of quasigeostrophic dynamics. People have considered this. These papers looked at the linear wave dynamics just on a state of rest and found that the linear waves seem to behave themselves. They agree with the sort of full shallow water system. It was looked at recently by Palder et al. In 2021 that looked at the linear stability of a jet and looked at the growth rates for shallow water can be smaller they found that the growth rates for shallow water can be smaller by more than 50%. And I think what they mean is that the growth rates for QG can be more than double shallow water. It's the same thing. So that doesn't bode well, maybe, right? Okay, that's quite a big discrepancy. That's all linear dynamics, and we can ask, well, supposing maybe you can get away with some of that if you're interested in full nonlinear evolution, maybe the linear wave dynamics somehow gets averaged out or is less important. So this is the comparison I'm going to show you. I was involved in test cases for shallow water some time ago, and there's a test case that looks at basically an unstable mid-latitude jet. So this is we define a U bar, a mean velocity varying in latitude. It's just a mid-latitude jet. And in shallow water, we start off with a balanced jet. So from that, you can get a vorticity and a height field and your potential vorticity. And then we just add an unbalanced perturbation. You need to do something. If it only depends on latitude, it's going to sit there. But if it's unstable, if you add a perturbation, the instability will grow. And then try to repeat this as closely as possible in the global QG framework. Okay, so you can prescribe a velocity field that's exactly the same as the shallow water one. That will give you a vorticity and a stream function, which is exact, and you can construct your potential vorticity. Of course, the quasi-geostrophic potential vorticity is not going to be the same as the shallow water potential vorticity. So, right? They're different functional forms. Maybe they're close. And then you can add a perturbation, again, in the vorticity. See what happens. So this is the jet. This is U bar. It's a narrow, strong, narrow jet. There's a height perturbation associated with that. This is the potential vorticity. The dashed line is the background planetary 2 omega sine phi, and then the solid and the dotted lines are the shallow water and the QG. The QG and shallow water are very close, first off. But the deviation from the planetary vorticity in this case is of the order of the planetary vorticity. So zeta and f are of the same order. Basically, Rossby number is order 1. Okay, so this is, you might consider it foolhardy to even attempt this, right? To attempt a comparison with QG. Rossby number is order 1. Okay, so the terms we dropped before we shouldn't have dropped. Also, the balance, the geostrophic balance, when U is that large, should really be something called cyclostrophic balance. There's a nonlinear U term that should really be taken into account. Froude number is a quarter, which is small, so maybe that's okay. And this is what the evolution looks like. So this is the whole sphere. The perturbation starts off around here. And what I'm plotting here is the divergence field, just at the very earliest time. So this is over the first few hours. And you can see a wave that propagates away from this disturbance. This is in the shallow water case. And this is an inertia gravity wave. So this is what they look like. They propagate relatively fast, so they've gone around half the planet in a few hours. They meet at the antipode, and then they come back. And they rattle around for a while. They don't really interact with the jet, which you can't see here. The jet has zero divergence. And yeah, that's the shallow water divergence. The QG divergence is 0 by construction. So the quasi-geostrophic model, global or not, doesn't capture any of this. You could say that's a deficiency. I say it's a bonus, right? We're not really interested in that in a lot of cases. If you're interested in the large-scale circulations. Okay, these are just waves that rattle around. So what about the balance dynamics? So this is the relative vorticity, zeta, after 4 and 5 days in the shallow water case. Nothing much happens up to this point. Normally, the perturbation starts off over here, and it's advected by the jet, and it grows exponentially, but it's weak until this time, and then things start to get interesting. Things wrap up. The red is the positive vorticity on the poleward flank, blue is negative on the equatorward flank. And after 6 days, which was the time in the original test case paper that we said this is a good time to use for comparing your shallow water if you're developing a new model. If you can capture all this strong nonlinear dynamics, then your numerical scheme is probably doing the right thing. And we looked at various numerical convergences and so on. So that's at 6 days, and that's the shallow water equations system. So there's dramatic effect here by waiting, keeping you in suspense. The QG, which I'm about to show, looks like that. And the first thing you say when you plot this is, I've plotted the wrong file, right? I've plotted the shallow water data again. I forgot to change the file name. Okay, you look at it for a while, and you think they're identical. So they're not identical. If you look very carefully, there are some differences, but they're hard to spot. Even little details like this seem to be captured fairly well in QG. This is Rossby number 1. Okay. So I showed my GFD students now this, and they say, why? What is happening? And you say, well, okay, this is on the globe. Maybe the latitudinal extent of this is still not that wide. Maybe we're getting away with things. It's mid-latitudes. What about putting this jet closer to the equator? What happens? Or increasing the Froude number. That was the one thing that was still small. So this is the same thing at the equator. That's the shallow water model. And the QG model looks like that. Again, you have to look quite hard to see any differences. They are different, right? This is in the tropics. There's the equator is there for minus 45 to 45. Okay, so that's not what you expect from QG. So what's going on? These are the difference fields, the shallow water minus the QG, just to show that they are different. But the differences in the tropical jet case aren't that bigger than the mid-latitude case. And the differences that do appear are mostly associated with just a shift of the pattern. Okay, so the pattern from one to the other has been shifted slightly to one side, and there are strong gradients, so you pick up a positive and a negative anomaly. Right? It's not big differences. So in the tropics, F goes to 0, your geostrophic balance breaks down. But another thing happens is that your deformation radius, which is sort of a measure of the effects of rotation and stratification, goes to infinity. And the larger the deformation radius, the closer the shallow water model is to just purely two-dimensional barotropic vortex dynamics. So I think what's happening in the tropical case is that both QG and shallow water are you're just solving the barotropic vorticity equation. Okay, there's not much effect of the height field. And that's borne out if you plot the height field, the height perturbation. This is the mid-latitude jet case, so there's some difference across the jet. In the tropics, that difference is much weaker. Okay, so it really just things look more 2D in that case. We can also look at larger Froude number. This is Froude number 0.5. And at that point, there are bigger differences to be seen. The growth rates in QG are possibly slightly smaller. I think the latitudinal extent here is less than there. Okay, so it looks like there are some differences, but you can't actually increase the Froude number that much more. And this isn't a restriction of the quasigeostrophic model, it's a restriction of shallow water. So you can't have your height field bottoming out. And the shallow water approximation itself is based on this h prime over h being small. Okay, so we shouldn't expect, maybe we shouldn't believe shallow water too much in that limit. Back to the Paldor et al., the 2021, that found larger QG growth rates. They actually only looked at the largest 3 zonal wave numbers, k equals 1, 2, 3. And if you look at the instability, it's dominated by, this is wave number 6. This is like wave number 8, 9. So it's the wave numbers, the most unstable wave numbers, they didn't consider those, right? So there are differences between, let's see, it's the green and the blue, and it depends on h. So our case was that h is 10 kilometers. The first one, the higher Froude number case, was 2.5 kilometers. But they're the wrong wave numbers to be considering. So if you do it properly over the full set of wave numbers, where the instability is stronger, wave numbers 8, 9, the agreement between the two is actually very good. And it's only down, let's say here, k equals 1, 2, 3 for the larger Froude number case where there is a difference. And larger QG growth rates here, but smaller QG growth rates at the top. So QG is growing more weakly. Okay? That's me at the conclusion, so I'll just wrap up quickly. We often say that QG does much better than it should, based on the formal asymptotics. But still, I was surprised by the level of agreement here. It captures the nonlinear evolution at Rossby 1 and in the tropics. In the tropics, I think I can understand what's going on. As f goes to 0, your deformation radius goes to 0, and it's basically 2D dynamics. Also a caveat, the choice of test case, this is a balanced jet. And in the tropics, a lot of the dynamics that we're interested in is not balanced. So I'm not saying use the QG model in the tropics. The QG model has no Kelvin wave, for example, and the tropical response to various forcings involves unbalanced dynamics. So QG is not going to capture those dynamics, but for a balanced jet, it does a good job. Okay, and you can use it on the sphere. So I like this partly as a demonstration for the GFD course. This is now in the course, and it's useful to illustrate the fast-slow dynamics and the ability of the QG model. But it's also a useful model to have. There are lots of global circulation questions where you might want to use a single layer model, but shallow water, you're not interested in all the gravity waves. So this is a handy model for that. Okay, so I'll stop there. Thank you.